Hey everybody, today the goal is to talk to you a little bit about conservation of energy. Now the hope is that you've learned a little bit about this in your past science classes, right? Maybe not in 9th grade, but maybe in 7th or 8th grade you learned something about different types of energy, conservation of energy, how it changes forms. But don't worry, we're going to go ahead and start from the get-go, from the very beginning, and talk about each of these pieces. Now, as we go through the video, I'm also going to include this in an ed puzzle, which means there's going to be some questions and other things for you to kind of think about what you're learning. But I want you to make sure that as you work through this, you're doing two things. One is you're answering the questions in the video, but you're also taking your own notes in your notebook so that you have access to that information at a later point in time. All right? Just like we just did the criteria BC assessment in class and you were allowed to use your notes, you were allowed to use your information, there's a possibility that those things will come in helpful. If not just in a homework assignment, then possibly on some type of assessment in the future. All right? So let's jump right into it. We are doing conservation of energy. We're going to be looking at kinetic energy, potential energy, and work. All right? So we're going to go start off with energy. What is energy? Well, the best definition I've found is this one. Energy is the ability to do work. Okay, now what is work is the next question. Well, work occurs when a force is applied in the direction of the motion of an object. Now when I say the direction of motion, I mean parallel to the motion. So if an object is being moved in this direction, its displacement is that direction. If I exert a force in this direction, or I exert a force against that motion, like friction, right? When something's moving one way, friction works the other way. Those forces would do work, okay? Now, usually work means if you're pushing on something, it's probably going to accelerate. Now, that's not always the case because maybe there's lots of different forces going on. But generally, the idea of work means that the object is going to be able to gain speed in some way, shape, or form, or lose speed, right? Now, let's go back to this idea of energy. Energy is the ability to do work. Now, there's different types of energy. The units for energy are joules, okay? It's made up of kilograms and meters and seconds, but to simplify things, we usually just say that energy has units of joules. Now, work also has units of joules, and we'll come back to that later, all right? Now, an object with energy can do work, right? We just defined energy as the ability to do work. So if something has energy, then it should be able to do this. It should be able to exert a force on an object to get it to move, right? Now, the opposite is also true. When work is done, it generally causes an object to gain or lose energy equal to the amount of work, all right? So, we can go back and forth. Now, we're going to try to dig in and understand that a little bit more. Now, the first type of energy we're going to look at is generally the easiest, right? This is kinetic energy. So kinetic energy is the energy of motion. Now remember, energy is the ability to do work, and work occurs when an applied force causes an object to move. So if you think about this, if an object is moving, if it hits another object, it has this ability, the ability to exert a force on something and cause it to move. Or if it's already moving towards you, then hitting it could cause it to slow down, right? To cause it to lose energy. But this idea of the kinetic energy is the energy of motion. If a moving object runs into a second object, it will exert a force and have an ability to cause that thing to move or to change its motion. That's what I was just talking about, right? Now, here's a video. Don't worry, it'll replay. I know it's standing in front of it at the beginning. But we've got a remote control car of some kind, right? The car is driving along. It's got some kinetic energy, right? Goes up into the air, it comes back down, it's got a lot of kinetic energy, and it runs into that girl there and knocks her over, right? That kinetic energy, the fact that it had that kinetic energy, gave it the ability to do work on the girl, to cause her to change her motion, right? That's kinetic energy. Now, given that that's what kinetic energy is, the next question is, what are the properties of that remote control car that might affect the amount of kinetic energy that it has, right? That energy of motion. All right, so hopefully what you're thinking about is, well, if that car is going faster, then it would have more energy, more ability to do work, right? To get that girl to change her motion, right? The other thing that hopefully you thought about is mass, right? If that car was bigger, then even if it had the same speed, then it would be able to cause a greater force and therefore cause her motion to change more. So those two things, mass and speed, both affect the amount of energy of motion, kinetic energy that that object has. So we put this together and it gives us our equation for kinetic energy. So the equation for kinetic energy is 1/2 mv squared, where m is the mass of the object and v is the speed of the object. Now I know it's very likely that your brain is saying v is velocity, but kinetic energy is not a vector, right? Remember, a vector has both direction and magnitude. The direction is important. Kinetic energy, the direction doesn't matter. If I'm going 10 meters a second in this way, I have a certain amount of kinetic energy. If I go 10 meters a second that way, I still have the same amount of kinetic energy. If I go up 10 meters a second, I have the same amount of kinetic energy. If I go straight towards you with a speed of 10 meters a second, I still have the same amount of energy, the same ability to do work, regardless of the direction that I'm traveling. And so therefore, kinetic energy is not a vector, and v is the speed of the object, not the velocity. All right? Now, we can use that to solve some fairly simple questions. If we have a student, 52 kilograms, running at a sprint with a maximum speed of 8.2 meters per second, we can answer how much kinetic energy she has, right? So we just learned that kinetic energy equals 1/2 mv squared. And so we can put in the numbers. We can go k equals 1/2 times the mass, which was 52, times the speed, which was 8.2 squared. And from there, we can pull out our handy dandy calculator and we can calculate. So we just go 1/2, which is the same thing as 0.5, times 52 times 8.2 squared. And when I do that, I get 1,748.24. Now these only have 2 digits, so when I write my final answer, I'm just going to round it to 2 digits. I'm going to go 1,700 joules. Remember, joules is the unit for energy. All right? So 1,700 joules, just like that. Okay? So it's pretty easy, right? If you're given the mass and the speed, all you have to do is put it in and you can get kinetic energy. All right? All right, let's go on. So we have the following information from a student's lab. Okay, and I did actually take this from one of y'all's labs. So the following graph shows a basketball about 0.625 kilograms rolling down a ramp. This was obtained from a student's graph. So here we go. I even included the picture with the slope and everything on it. This is a velocity versus time graph. All right. Now the question is, determine the maximum kinetic energy of the ball. All right. Well, we know that kinetic energy equals 1/2 mv squared. Now we know the mass is 0.625. So K equals 1/2 times 0.625. And now I need the speed. Now to get the maximum kinetic energy, I'm going to want the maximum speed. And so I'm going to look in my graph and I'm going to find the place where I have the maximum speed. Now remember, speed and velocity are very similar to each other. Distance over time, displacement over time. But the ball was going in a straight line, which means the distance and the displacement were the same. So therefore the speed is going to be the same as the velocity. It just won't have a direction on it. And so my maximum speed is going to be the place where I have maximum velocity. So I'm going to look for that and I'm going to see, that looks like right here. That looks like the maximum velocity that I have. And so now I'm going to pull out a meter stick and I'm going to draw a line. So I'm going to try to follow that graph here. Obviously you won't need a meter stick. It's on your paper there. But if I try to draw a line straight up from there, it looks like it's pretty close to 0.5, 0.6, 0.7, 0.8. 0.8 meters per second. So I'm going to go ahead and put that in. I'm going to go 0.8 meters per second and then square it. Now I can handy dandy calculator. So 1/2 times 0.625 times 0.8 squared, and I get 0.2. All right, so my kinetic energy is 0.2 joules. There we go. So a little bit harder, right? But not that bad. All we had to do is look at the graph and find the speed. All right, let's try one more. Okay, this one will be a little bit harder yet. And you notice already, right? You can see down there my kinematics equation, my SUVOT, right? It's all right. Here we go. Let's see what we can do. All right, so in a sport called zorbing, this is actually a real sport, you enter a large inflatable ball and roll down a hill. In one instance, the ball starts at rest and takes 7.6 seconds to roll down a 50-meter hill. Assuming constant acceleration, what kinetic energy will it have at the bottom of the hill if the ball and the person inside have a mass of 90 kilograms? All right, now the first thing we would think about probably is, well, I need kinetic energy. In order to do kinetic energy, I need 1/2 mv squared. So I've got the mass. The mass given was 90, so that's 90 kilograms. So I can go K equals 1/2 times 90. And now I need the V, the speed. Now, that's not given to me, but I did give you a hint, right? And you can see in the question there's some information about time and displacement, right? So I think we can use that to help us find the speed. Let's see. Let's see if we can figure it out. So what information do we have? Let's write down our SUVOT. S-U-V-A-T. I know that my displacement is going to be 50 meters. I know it says it starts at rest, so my initial speed is 0. I'm looking for the final speed. I know some of you saying, oh, I know Mr. Bauer, acceleration in -9.8. Nope, it's only -9.8 if it is falling straight down, right? This is like your lab, the ball is rolling down a really big ramp, right? And we found in the lab that as it rolled down the ramp, the acceleration was less than 9.8. So don't jump straight to 9.8 being the acceleration. It's going to be something else. We actually don't know what it is. But they do give me the time. The time is 7.6 seconds. So that was meters per second. This was meters. Okay, and I don't have the acceleration, and I'm not looking for the acceleration. So what I'm going to do is I'm going to find the equation that does not have acceleration in it. The acceleration without acceleration is this one right here. So I'm going to go S equals U plus V over 2T. And so now I can put the numbers in. I can go 50 equals 0 plus V over 2 times the time, which was 7.6. All right, I can do a little bit of simplification here. So 50 equals V over 2 times 7.6. So I'm going to go ahead and take my 50, and I'm going to divide by the 7.6 first. And then it's V divided by 2, so then I'm going to multiply that result by 2, and I get 13.15. So I'm going to go 13.2. So V equals 13.2 meters per second. So that'll be my final speed. And you may say, well, that's not very much. Actually, 13.2, that's, I don't know off the top of my head, but that's pretty close to 40 kilometers an hour. That's pretty fast for a ball rolling down a hill with a person inside of it. All right, so 13.2, we'll go ahead and put that in for our velocity. And remember, that is squared. And so now I'll go 0.5 times 90 times that 13.2 squared, and I get that K equals 779 joules. Ta-da! All right, so that was level 3. A little bit harder, right? We had to involve some of our kinematics in there, but we were able to do it, right? Now, we may learn some other ways to do that later, but for now, we'll go with this, all right? Hopefully, that wasn't too bad. Now, I'd like for us to dig a little bit into this kinetic energy, because usually when we talk about kinetic energy, we're talking about the macroscopic picture, right? The big picture. We're talking about the object as a whole, right? That object as a whole is rolling down a hill, or that object is a person that's running straight, right? So we're looking at the object as a whole, right? But in reality, individual particles can have kinetic energy too. In a gas, those particles are flying all over the place, right? The air particles right now are all flying all over the place, bouncing off of each other. They've got a lot of kinetic energy, right? In fact, even the molecules in your body, the atoms in your body are vibrating, right? That's motion too, that's kinetic energy. Now that type of kinetic energy, we generally refer to as thermal energy, right? It's still kinetic energy, but we will refer to it as thermal energy to differentiate. Because we'll often talk about that kinetic energy, the big motion of the object. That's something we would call mechanical energy. That's something due to the mechanism as a whole. However, thermal energy is due to individual particles and all that energy added up, all the vibrations and moving of the particles. So in this class, we're not going to talk about this thermal energy very often, other than the fact that sometimes the kinetic energy of motion can be converted into thermal energy, right? You might be able to feel this when you run into something. You can feel like a vibration, right? That vibration moves into your particles and causes them to move. And we'll talk about that a little bit more. Another type of kinetic energy that we often refer to a little bit differently is sound, right? And you may say, well, how is sound kinetic energy? Well, sound occurs when a vibration causes air particles to move. And when those air particles move, they bump into other air particles, which bump into other air particles, until finally those air particles bump into your eardrum, and they cause your eardrum to vibrate, and then your brain interprets that vibration as a sound. So sound is really vibration, which is motion, which is kinetic energy, right? But again, we will normally not talk about sound as kinetic energy, because when we talk about kinetic energy, we're talking about the bulk motion. We're not talking about particle motion, microscopic. All right? So just wanted to make sure we got those ideas. So now we've actually talked about three different kind of types of energy. The bulk kinetic energy, that 1/2 mv squared. Thermal energy, which we often feel as temperature or heat, kind of we describe it that way. Those are all different things, but the ideas are kind of similar. They can be confusing that way. And then, of course, we got sound here, which is the vibration of the air particles and causing you to interpret a sound. Now, let's step away from kinetic, the motion of energy, for a minute. Let's talk about potential energy, right? Now, there's actually a lot of different types of potential energy, right? Generally speaking, any energy that's not kinetic is probably potential, right? So if it's not that bulk kinetic, if it's not sound, if it's not thermal, chances are it's going to be some type of potential energy, right? Now, potential energy is energy that is held in a system, so multiple objects, 2 or more objects, due to the location of the parts of that system. Now, a couple of examples of this are gravitational potential energy. And you may have heard that one before, right? Gravitational potential energy is due to 2 objects that have mass that are attracted by a gravitational force. Now, because there is that interaction between the 2 objects, depending on how far they are apart, they will have a certain amount of potential energy. That potential energy, as they are attracted together, can turn into kinetic energy, right? And so therefore, gravitational potential energy is due to the location of 2 objects and the gravitational force between them, an interaction between them. Another type of potential energy that we will use, we'll often talk about this last one, I'll come back to electric, but elastic potential, right? Elastic potential energy is when you have an object interacting with an elastic object, something that you can stretch, and when you release, it goes back the way it was, like a spring, or a slingshot, or a rubber band, right? Or something like a bouncy ball. When the bouncy ball hits the ground, it compresses against the ground, and then because it's elastic, it goes back to where it was. And when it does that, it stores and releases elastic potential energy. Now, all that has to do with the position of the particles, the position of the ball, the position of how, you know, the slingshot and the rock interact with each other, right? So it's something that has that elastic force, but then how does another object interact with that? That is elastic potential. The position matters, right? The further you pull that slingshot back, the more potential energy it has, okay? Now, electric potential is due to the separation of objects that have charge, right? So you should have learned a little bit about that last year in 9th grade. If you have two positive particles, they push away from each other. The closer that you get them, the more that they push away, right? Now that then connects to this idea of there's an interaction between particles, and depending on what their position is, they have a certain amount of energy that is stored, right? They store this energy. We often say that potential energy is potential to have kinetic, but I like this idea of talking about an interaction between particles or between objects, and secondly, talking about the fact that the position of those objects matters. And we'll see that as we talk about these different types of energy as we go forward, all right? So let's talk for a minute about gravitational potential energy. Now, I've included a short video, a short GIF, I guess, of somebody from my university, BYU, which is pretty awesome. You may have, if you watch college sports, they're doing really well in football this year. They're doing really well in girls soccer. They're doing really well in basketball. So anyway, I thought it was fitting to put that in here. A little shout out to BYU. But what you can see is that as she holds the ball out, it has what we call gravitational potential energy. Now that the ball doesn't have gravitational potential energy. The ball and the Earth system have gravitational potential energy. Now that is because of the gravitational interaction between them. As they interact with each other, then there's a certain amount of energy stored there, and if you release the ball, then that stored energy can turn into kinetic energy. Now that's due to the interaction between them, the force, the gravitational force, and the position of the object, right? The higher you hold the object, the more kinetic energy it can gain as it falls, so therefore it must have had more potential energy to start with, right? Now, this is the basic idea. Due to the position of the ball, it will have a certain amount of energy that it's holding inside of it. The higher it is, the more kinetic energy it can get, therefore it must have had a higher potential energy. So that's essentially what I just talked through initially, all right? It's just written out. Now, here's the equation that we will use in this class, okay? So we use a U for all of the potential energies. So UG is gravitational potential energy, and that is equal to mgh, where m is the mass of the object, g is the acceleration due to gravity, and h is the height above your 0 point, all right? So that is how we will calculate it. Now, the reason why I say the height above your 0 point is you can choose where that 0 point is. Right now, I'm in the science room, which is on the 3rd floor of this building, yet I don't have to use the absolute ground as my 0. I can say that the floor of this room is my 0 point. And so I can just say that the height of my ball, if I held it at about chest height, it would be 1.5 meters. I don't have to include the distance all the way down to the ground outside. That makes sense because, well, what do you do if it's down in the basement, right? You have to be able to go below that 0, so that's not really 0 either. 0 would actually be the center of the Earth because then you can't go any lower than that. But rather than have to worry about that, you can define your 0 so that you can determine how much gravitational potential energy something has. All right, so let's do a quick example. Again, we'll start off easy. Determine the gravitational potential energy of a Zorb ball that has a mass of 90 kilograms if the hill is 50 meters tall. Now this is a little bit different from the other question. Before I said that it was 50 meters down the path. Right now we're going to say that the hill is 50 meters tall, just to kind of simplify. So we're going to go UG equals mgh. All right, so gravitational potential energy will equal the mass, which remember we said the mass was 90. That was in the previous question. Oh yeah, 90 kilograms. G is the acceleration of gravity, 9.8. Remember that g is not inherently negative, just when we need it to be a vector. Energy is not a vector, so we don't need the negative here. And then the height will be 50 meters. And so now I should be able to put all that together. And so I'll go 90 times 9.8 times 50, which gives me 44,100. So gravitational potential energy equals 44,100, and it's energy, so it's still joules. All right? So not all that difficult if we just use the information given to us, right? Okay, let's look a little bit deeper at this. Now, gravity is what we call a conservative force. Now, let me give you a couple of ways to think about conservative forces, okay? One way is this. If you start with your ball on the surface of Earth, if you move it up, we talked about the fact that it has more potential energy. We can get that from the equation. We can get that from the idea that the higher it is, the faster it can go, the more kinetic energy it can get. So, as it goes up, it gains potential energy. Now, as it goes down, as it goes in the opposite direction, it loses potential energy, right? If I start at the ground and I end at the ground, then it has the same potential energy that it started with. That means that it is a conservative force. So the two things we're looking for is if we go one way, energy does one thing, and if we go the other way, the energy does the opposite, right? Go up, energy increases. Go down, energy decreases. I'll give you some examples later of things that are not conservative, and it'll make a little more sense. Secondly, if I start at the ground and I do a bunch of stuff, even if I move it side to side, throw it up in the air, whatever, if I end up back on the ground, back where I started from, if it doesn't matter what path I followed, if I still have the same amount of energy, then it's conservative. Same thing, if I start on the ground and I go up 1 meter, it has a certain amount of gravitational potential energy. If I start at the ground, I go up, I shake it around, and end at 1 meter, it still has the same amount of gravitational potential energy. It doesn't matter how you get there. All that matters is the end point. That makes it a conservative force. Gravity is a conservative force. Therefore, gravitational potential energy, when we include it in our system, is conservative. All right? It can be conserved. It stays the same. All right? We'll talk about that a little bit more as we go. Okay? Now, this is essentially the first law of thermodynamics. The first law of thermodynamics says energy is conserved. That means you can't create energy from nowhere, right? It has to come from something. It has to come from some other form of energy. In addition, you can't destroy energy, right? Whatever energy you start with, you got to end with that energy unless you bring in energy from some other form of energy, okay? And I'll try to give you some examples of this later as we kind of go through this. A great example of this is a roller coaster, right? If there's no friction on a roller coaster, then we start at the bottom, and at the beginning, a track pulls the roller coaster up. Now that pulling is a force doing work. Remember we said that when a force is in the direction of motion, it does work. So as we pull it up, it gains potential energy. It's going higher. But once it gets to the top, there's no more force pushing it up. Now the only forces are gravity, which is conservative, and then the normal force, which is always perpendicular to the motion. And one of the things that we'll find is that when forces are perpendicular, they don't actually do work. We'll come back to that hopefully at some later point. But we get to the top, we have maximum potential energy. As the roller coaster goes down the ramp, we can see the potential energy is decreasing, but it's speeding up, so the kinetic energy is increasing. And by the time it gets down to the bottom where potential energy is 0, all of that potential energy, you can see it was 1, 2, 3, 4, 5, 6, 7, 8 bars worth. All of that has now turned into kinetic energy, which is 8 bars worth. Now, realistically, some of that energy is probably lost due to friction, right? There's sound, there's heat, there's different things happening. So we're probably going to lose some of that energy. But if we're not losing it due to work, if we say there's no friction, then we can say that energy is conserved. Whatever energy we start with, we have to end with unless there's something taking it out, turning it into a new form. Energy is never lost, right? We may say energy is lost, but what we mean is we can't use it anymore. Maybe it's turned into the vibration of the particles, thermal energy, right? Or it's turned into vibration of the air particles, sound, right? If it turns into those forms, that energy is gone. It's somewhere else. We can't use it anymore. All right? So let's continue. This is an example of, I'm from Texas. This roller coaster that I'm about to show you a video of is a video of, let's see, where's my cursor? The Texas Giant, which is a wooden roller coaster at Six Flags. So we can watch this. So thinking about energy conversions, right? One of the things to recognize is right now, it's being pulled up the hill, right? So the chain is exerting a force, pulling it up the hill. So the chain is doing work, causing it to gain gravitational potential. Now it gets to the top, and now it's going to let it go. So as we go down, the gravitational potential energy is turned into kinetic. Now it's going fast, right? It's got a lot of energy in motion. As it goes up, you can see it's slowing down again. That kinetic is turning back into gravitational potential, and that just goes back and forth and back and forth and back and forth, right? And that's what we're seeing. As it goes up, kinetic energy is turned into potential, and as it goes down, the potential is turned into kinetic, the energy of motion, right? Now, in a real ride, there's very often a place in the middle where they start pulling you up again because energy isn't perfectly conserved, right? We can talk about conservation of energy. We can say that work is done when it's being pulled up, but really throughout the ride, there's friction that is opposing the motion, and that is in the direction of motion. It's just opposite, all right? So friction is taking energy out. Friction does what we call negative work. Negative work means that energy is being lost. It's being taken out, right? And so very often that's happening. So in a real roller coaster, you'd eventually have to pull up again so that you can gain more energy, right? Do more work, gain more energy for the ride, okay? Now, talking about friction, this brings us into the idea of non-conservative forces, right? I talked about gravity as being conservative because no matter what, if I end in the same place, I end with the same gravitational potential energy. If I go up and go down, I gain energy one way and lose energy the other. Let's talk about some of these other forces, right? A good example of a non-conservative force would be tension, right? If I take tension and I pull it in one direction, it's going to gain energy in that direction, right? If I then take the string and I pull the other direction, it's going to gain energy in that direction, right? So whatever direction I'm pulling, it's going to do positive work in that direction. And so it's not like gravity, which was gain energy one way, lose energy the other. And so depending on how I pull, my object will gain or not more or less energy, right? Friction is the opposite, right? Friction is if I move this way, friction opposes me and I lose energy. And then if I slide the object back the other direction, again, friction opposes it and I lose energy again, right? So these are great examples of non-conservative forces because I'm going to lose energy. If I drag my box a certain distance, there's a certain amount of friction and I lose a certain amount of energy. But if I take that box and I slide it along the desk and I take a much longer path and end up in the same place, I'm going to lose a lot more energy because I'm going to have friction for a lot more time. Therefore, friction is non-conservative because the path matters. The path matters, and pulling it different directions actually causes the same effect, to lose energy for friction, okay? Now, normal force is similar, right? If I push it this way, it gains energy that way. If I push it that way, it gains energy. Right? It's a gain no matter what, as long as I'm pushing in the direction of the motion, okay? So, therefore, hopefully that clarifies a little bit of conservative versus non-conservative, all right? We're going to look at one other conservative force here, which is the force of a spring, right? Now, if you think about the force of a spring, you have a spring. If you squeeze the spring, then now it's what we call compressed. And when it's compressed, where does it want to go? If you think about pressing a spring, you push it in. Now, if you were to release it, it goes back to where it started from, right? Most elastic objects try to return to a point of equilibrium, the point they were at before. Same thing if you take that spring and you pull it like a slinky, right? You pull it out and you release it, what happens? It goes back to where it started from, right? So elastic potential energy is energy that is stored in a system of objects, so the spring in the block, or spring in your hands, or whatever it may be, due to the stretch or compression of an object. Now, remember, that means that it has the ability to do work. If you put the block on the end of a spring, you compress it, you let it go, the spring will push the block, and the block will gain kinetic energy. Now, one of the cool things about elastic potential energy is that a spring, much like gravity, is conservative, right? If I push a spring this way, then the spring gains elastic energy. But if I then release it, it now loses energy, right? It doesn't matter whether I compress to this distance right away or if I compress further and then come back to that. If it has this distance, then it has the same amount of energy regardless of how I got there. That makes it conservative. So because of that, we have another formula for elastic potential energy. Now, for elastic potential energy, we are going to use US. Now, that may seem a little weird because we used UG for good gravitational, and elastic does not start with S. But the problem is that, remember I mentioned electric potential energy earlier due to the charges? That's going to be our E. So very often we use US, kind of like a spring, for our elastic potential energy. And that's 1/2 kx squared. Okay, now K is a spring constant. The spring constant, don't worry too much about it right now, but it's related to how stiff the spring is, right? If it's harder to pull, it takes more energy to pull, you're going to have a higher K. That K depends on a lot of things. The material of the spring, how long it is, how big the coils are, how thick the coils are, right? A lot of things go into that. So we're not going to go into the details of that. I'm not going to be like, here's a spring, what's K? Well, in order to get that, you would do some tests with force, you do some tests with the elastic potential energy, and you might be able to figure out K that way. But you're not going to have to just be able to look at it and make some measurements and figure that out. That's not how it works, okay? So don't worry about that. This will likely be given to you, or you'll be given everything else and have to calculate it, okay? Delta X is the displacement of the spring from its rest equilibrium position, right? So when you lay the spring down, it has this resting position, okay? When you take one side and you push it, that distance right there, that's delta X. How far did you push it from that equilibrium point? Because that's where the spring's gonna go back to, right? When you release it, the spring goes back to that point, okay? So that is the delta X, okay? Now, quick example, 1.2 kilogram block compresses a spring with K 3.5 newtons per meter, a distance of 0.34. All right, so how much elastic potential energy is there? Well, let's go. Elastic potential energy is 1/2 delta X squared. So K is 3.5. And it says that it is compressed 0.34 meters. That is squared. And now I should be able to type that in to my handy dandy calculator. 0.5 times 3.5 times 0.34 squared. And I get 0.202. All right, so 0.202 joules. You could go 0.20 if you wanted because I do only have 2 digits here. But there you go. All right, still energy, still joules, right? You'll notice that that's pretty small. If you want more energy, you need a stiffer spring, right? You need a spring with a higher spring coefficient, all right? That's it. That's basically the idea of elastic potential energy. Now, as I mentioned before, I already answered this question, didn't I? Is the force exerted by a spring conservative or non-conservative? And we talked about that on the previous slide. You stretch it one way, it gains energy. You take it back the other way, it loses energy. That means it's conservative. You get to a certain point, it's the same amount of energy, right? This displacement is all that matters. The distance that you stretch it, how many times you stretch it, none of that matters. All that matters is how far is it from that original point, okay? Conservative force. And that's where we're gonna finish for today, all right? So hopefully that's helpful in introducing some of these ideas to you. I'll make another video later. In the other video, we'll talk about conservation of energy. What is that? How does that work? What does it mean? How can we use that in calculations to determine information? So we'll come back to that shortly. But in this video, hopefully that's enough to get you introduced to the ideas of kinetic energy, gravitational potential energy, elastic potential energy, work, and the beginning of the ideas of conservative versus non-conservative forces. All right? Okay, that's it for today. We'll see you next time.